In this video, we'll be looking at logarithmic functions and their graphs. Logarithms are just the unknown power when they give you the base and then they give you the answer. It's you figuring out what is the exponent. So the formal definition is given here, but for a couple quick examples, this first one is saying 2 to what power equals 8. So you would be saying it's the third power. That's what the logarithm is. For another example, 3 to what power equals 9? The answer to that is 2. So the logarithms are just the exponent to go from the base to the answer here. Now there are two special logs that we will use frequently, and you need to be able to recognize when you see them written out. This is a log base 2, this is a log base 3. If you don't see a base in the logarithm, then it's an imaginary base 10 there. Just like we don't write the first power or we don't write the second root. If you don't see a base on a log, then it's base 10, and we call that the common log. The other one to recognize is if they write this ln of x. This one also does not have a base written, but it is still a logarithm. It's a logarithm with a base of e, which is that number 2.71828 that we talked about in a previous video. This one is called the natural log, and I know it seems weird that they didn't do NL, they did LN for natural log. That's because in the language of origin, they flipped the noun and the adjective. So they were saying it as log natural for natural log as we pronounce it in English. The common log is definitely the most important and most frequently used one. These are both keys that you'll find in your calculator that we'll be using as well. Usually we use the base 10 one. We only tend to use the natural log one when there are e's involved in the equation somewhere. Since logarithms and exponents are essentially the same thing, sometimes we'll find it useful to rewrite an expression either from the logarithmic form to the exponential form, or vice versa, to go from the exponential to the logarithmic. Now there are some conditions to be able to use these properties, but I'm not going to be giving you weird setups for these where I give you a negative b value, for example, so you shouldn't have to worry about these conditions for the time being. So this statement says that the log base b of x equals y. And if you haven't seen this abbreviation before, that stands for if and only if b to the y power equals x. So this is essentially a matching game. You're going to say the base of the log is the base of the exponent. The number by itself for the log, which I use the variable y to represent here, is going to be the power when you rewrite it in exponential form. And whatever you were taking the log of, it might not just be an x, it might be a whole expression like x squared plus 3. That's what will go on the other side of the equation by itself when you rewrite it in exponential form. So let's look at a couple quick examples of going from log to exponential and exponential to log. So here the base b, so it's going to be 4 to a power if I write it in the other form. The number that's by itself on the other side, that's the y when you're in the logarithmic form, that goes up to the exponent of the base. So now I know that this is the third power. And then on the other side of the exponential equation, that's where x goes. X was whatever we were taking log of in the logarithmic form. So in this case, 64. So these are equivalent statements. One's just written in logarithmic form, one is written in exponential form. They each will have their advantages depending on what number is not given that you were solving for. And this one I gave you all three numbers so that you could see the rearranging. Now to go backwards, so this time we're starting with this side. So b is 5, and then that's going to be the base of my log. So I would write log base 5. Next, I have the exponent of y. That's the number that's going to go on the other side by itself. The order you do these things in doesn't really matter. I'm just trying to go from left to right. So I'm going to have equals, and in this case, my exponent was a 2, so I'm going to say equals 2. And then the number that was by itself, that's my x. That's what comes after the base. So now I have a written larger 25 after the 5. On the next slide, we'll look at some examples where I haven't given all three of the numbers, and we'll see why changing a log to exponential form can be useful to solve it. Many times this strategy will involve 3 steps: changing an exponential form, then trying to rewrite both sides of the equation as the same number being raised to different powers, and then you'll set those exponents equal. The common bases will cancel out if you can write both sides using the same base. So here we have some examples where we do not know what the exponent is. Sometimes you might be able to figure it out just by looking at it, but I'm going to show you the formal process anyways. So in this case, we do not know what the log base 2 of 32 equals. So I'm just going to say equals x for now. So that's my unknown value. So to rewrite this in exponential form, I'm going to have 2 to the x power equals 32. That's me rewriting logarithmic form to exponential form just by playing that matching game of which number goes where. Well, I believe 32 is a power of 2. So since I have 2 to a power on the left-hand side, I want to try to rewrite the right-hand side as 2 to a power as well. So you would need to sit there and figure out 2 to what power equals 32. If you can rewrite that right-hand side using the same base, so I have base 2, then I'm saying you can set the exponents equal and solve that equation instead. So this equation is done. It's just x equals 5, but sometimes there may be some extra adding or subtracting that you need to do. Now, a quick comment, I will point out that I will not usually write a log base 10 because I told you on an earlier slide that when you don't have a base, that's assumed base 10. But for this first example, before you guys have really mastered those properties, I wanted to write that this is going to be a log base 10. Just remember that if you don't see a base, that's what you'll have. So again, I don't know what this answer is offhand without writing out the equation. So to change this to exponential form, I'm going to have 10 to the x power equals the third root of 100. Since we have 10 to a power on the left-hand side, we want to see if we can rewrite the right-hand side as 10 to a power as well. And this is where some of your fraction exponent properties will come in handy. So 100 is equal to 10 squared. So when you have a radical, don't forget that the exponent on the inside, that's the numerator of the fraction exponent. The denominator of the fraction exponent is the index. If you don't see a number here, then it's a 2, but in this case, I have a 3. So the third root of 100 is the same as 10 to the 2/3 power. Don't forget those fraction exponent properties. Now that I have 10 to a power and 10 to a power, I can just set the exponents equal, and there's nothing else to solve here, so I'm all done. For the last example, I am using another one of those special logs to recognize. If you see an ln, then you need to know that this one is base e. So even though I don't see a base, since I know it's a natural log question, I have to recognize that this one in exponential form is e, and then it's going to be to the x power equals 1 over e cubed. So e is just a number like 2.718. It doesn't really matter though. We want to see if we can rewrite both sides as e to a power. So the left side is fine as is. But here it's handy to remember that negative exponents can be used to flip something from the bottom to the top of a fraction. So 1 over e cubed is actually the same as e to the negative third power, which means that now I have x equals negative 3. Here are some additional properties for logarithms that will help simplify many of the uglier expressions, followed by the explanation for why they are true. So anytime you have log of any base and it's taking log of 1, then the answer has to be 0. So if they don't tell you what this number is, I'm saying you know it has to be 0, because in exponential form you're saying b to the 0 power will equal 1. If you have something like log base 2 of 2, then this number has to be a 1. Because changing it to exponential form, that's the only way to go from 2 to what power still equals 2. It has to be a 1 in this case. So when the bases match, the answer will be 1. These are the two most important ones because they simplify the most for us. The easiest way to summarize these two statements is to say if you have log base 3 and then 3 to a power, or whatever the number is, as long as the numbers match, then the log and the exponential part will cancel out, and your answer will just be the exponent that's off to the side. The same thing works the other way around. If instead of going from log base b of b to a power, if it flips it and does b to a power of log base b, again, as long as those numbers match, whatever they are, if they're both 7, for example, then that stuff will cancel out, and your answer will just be whatever number you have here instead. So the explanation for why those are true is here. And here I've just written out that summary that as long as the base of the log and the base of the exponent match, they cancel. There's no work to really show you here. This is just some demonstrations of me applying those properties. Here I have log base 7 of 7 to a power. So if that stuff cancels, the answer will equal 13, the other number. Now I have it flipped. Now it's 8 to a power, and then the power has log base 8. Since again, the base of the exponent and the base of the log match, that stuff will cancel. So the answer here is just the 4.2. Sometimes they'll try and catch you with these again, so don't forget that natural log means base e. So I have a log base e of e to a power. So again, the base e for the log and the exponent cancel, which means my answer is just the square root of 2 part. So there's not really much work to show there. It's just a demonstration of how to apply those properties, what the questions would look like if you can use them. Now we'll look at the graph of the log functions. Now here I am just showing the log base 10 version, but that's because all of the other logs, whether it's log base e, which we call natural log, or log base 2 or log base 3, they all look basically the same. It's a very minor change from one logarithmic graph to the other. This is the same thing that happens with the 2 to the x and 3 to the x and 4 to the x. They all look basically the same. So good facts to know. This graph has a domain from 0 to infinity. It does not actually hit 0. It just approaches 0 on the left-hand side. So that's our x values from left to right. Our range, however, goes from negative infinity to positive infinity. It looks like it's approaching a horizontal asymptote, but it's not. It's still increasing forever. It's just that it's increasing slower and slower as you go out to the right. There is a vertical asymptote at x equals 0. That's what's preventing the graph from hitting 0 or going to the left-hand side of it. So you can't take log of a negative number, for example. And there is no horizontal asymptote. That's why this graph goes up and down forever. Our normal graphing transformation rules can again be applied to any of the logs, whether it's log base 10, log base 2, even natural log of x. So I'll show a couple quick examples of these specific applications. So when you see numbers being added or subtracted, these are your shifts either up, down, left, or right. Don't forget that the horizontal shifts, the ones that are inside the parentheses, these do go backwards from what most people expect. So having a minus actually means it's going to the right 2 units. For the stretches and shrinks, these are caused by having a number multiplied. If it's a number inside the parentheses, again, this will be backwards. So having something like log of 3 times x actually means that it's a shrink by 1/3. So you take the reciprocal of this number for the horizontal stretches and shrinks. And then for reflections, you could either have the negative in front of the whole function, or you might have the negative just on the x inside of parentheses. That'll change whether you're reflecting about the x-axis or the y-axis, which is sometimes called a vertical or a horizontal reflection instead. So the way this will look on a test or an assignment is they'll give you the original function, and then they'll ask you to transform it into a different function. So you'll see different numbers being multiplied, added, or sign flips on there. Since this one has a 1/2 multiplied out front, I know that that's the vertical stretch or shrink. The fact that it's a fraction 1/2 is what's causing it to be a shrink instead of a stretch. Next, the negative sign, since it's not in front of the whole function, it's just on the x value, which is our horizontal reflecting. We call that a reflection about the y-axis in this case. They may also ask you to sketch the graph yourself, or maybe even just to identify which multiple choice option matches yours. These stretches and shrinks will be hard to kind of show graphically, but you should be able to do any of the shifts and the reflections in this case. So I'm going to take the standard log shape and then just flip that one around to look something more like this. And that's it for the lesson on logs and their graphs.